we learned about the derivative as a function, and I want to make a short video about notation, which is like, what symbols do we use to represent derivatives and talk about derivatives? There are a lot of them. There are a lot of different symbols, and we need to use all of them. You need to learn them all because you'll see them in different contexts, and so you just need to know all these different notations. And the notations stem from different mathematicians. So a little bit about the history of calculus. Mathematicians: Isaac Newton, who you may know about because of his work in physics, a British mathematician, and Gottfried Leibniz, a German mathematician, or maybe Austrian, I can't remember. I always get that. Hang on a second. Leibniz, where are you from? German. Yeah, he was German. So the two of them both sort of invented calculus independently in the late 1600s, early 1700s, that sort of era. There was some debate about which of them did it first. They both did it independently and in slightly different ways. They both are very significant contributors to the development of calculus in its early days. And they used different notations, and those notations have both survived to this day because they're different, because they have different values that are very useful in different contexts. The third mathematician is Euler, who came a little later, and Euler contributed to a lot of different fields of mathematics, but his contributions to calculus involved introducing yet another notation, which I think is a bit simpler. It's my favorite of the three. Anyway, I'm going to teach you all of them. So far, what I've taught you is f prime. Okay, f prime of x. That is a form of Newton's notation. You can also write y prime, which is just if we already know that y depends on x as a function, y prime means the derivative of y with respect to x, the derivative of that function. The prime means derivative with respect to x. That is implied based on context. Newton actually originally used a little dot above instead of a prime. It evolved into the prime notation. So we basically call this is basically Newton's notation. Now, one thing we're going to learn soon is that you can have the derivative of the derivative, the rate of change of the rate of change. To give one example, if you look at the rate of change in position of an object moving over time, you get velocity. The rate of change in velocity over time is acceleration, getting faster or getting slower, deceleration. So that's the derivative of the derivative. And so for Newton notation, we can just increase the number of primes. F double prime, we call that. And you can do that on the y if you want to as well. Leibniz notation is a little bit different. Leibniz notation evolved out of the idea of the secant slope being delta y over delta x, like that. That's the secant slope, and then as delta x approaches 0, you get a tangent slope. So Leibniz notation comes from that. It looks like, well, one of the ways to write it is dy over dx, like that. It looks like a fraction. In a sense, it sort of is a genuine fraction. But remember that the delta x is approaching 0. We're not literally dividing by 0. That's not what's happening here. So don't really think of this as a fraction of numbers. The dy and the dx represent very very small changes in x, infinitesimal changes, infinitely small, that is. So we'll talk more about that later this semester when we get to the topic of differentials in chapter 4. But for now, you can think of that as one symbol that means the derivative of y with respect to x. This is useful because you can talk about the derivative of something with respect to different possible independent variables. Like, here's the derivative of y with respect to time. In physics especially, derivatives with respect to time versus derivatives with respect to position are different, and they have different uses. different purposes. And so it becomes important to like point out which variable you are sort of measuring against, which variable are you holding steady and comparing to, and that's the one in the denominator. So Leibniz notation has the benefit of making that explicit. You can also write it with the function name f. You can write df over dx and even put like a of x here, like that if you want to. Or you can write it like d over dx and then put the f on this line like that, sort of like in the middle, like it's being multiplied, sort of not being multiplied. It's more like applying a function multiplying. But that's a couple ways of writing that. And then for higher derivatives, which I'll write on at the end here, we write it like this. Say you want to do a second derivative, you do d squared y over dx squared. And you can do d squared over dx squared and then f. I'll talk about why it looks like that in a minute here. So that's the Leibniz notation. Euler notation looks like this. Euler said, let's just say you're doing a derivative. Let's use a capital D for derivative. And then let's use a subscript to specify which variable you're differentiating with respect to, whether it be position, time, whatever, right? And so he says, put the x down here as a subscript, and then write that next to the y. Or perhaps, yeah, well, like that next to the y. And then that means derivative with respect of y. Or derivative with respect to x of f. And then that whole thing is the name of the function. It's like equivalent to f prime. So you can say of x if you want to specify what its input is, right? Or you want to like write it as a function. So those are the three notations. Now underneath here I have a second row for differential operator. What is a differential operator? Okay, if you have a function and you do its derivative, you want to give that derivative a name. You can call it y prime, or you can call it like f prime of x. But what if you're just sort of, what if you want to use the idea of differentiation as a process, and you want to use it on the fly without having to like give the function a name? Suppose you have an expression and you just want to perform the derivative on that expression. Like let's say you have x squared plus 3x plus 1. And you just want to do the derivative of that. And you don't want to have a name for that. You don't want to have to be like, oh, let's call this f and then call it and then say f prime. No. A more fluid use of the derivative as a process. What you can do is use something that first of all is called a differential operator. You want some sort of notation that says get the derivative of this input expression. And in this is not very common. Newton notation is not very good for this purpose. But if you put brackets or parentheses around something, then put a prime on the outside like this, it looks like you're raising it to the power 1, but this means this is prime. Okay, it's a little bit different. That can be used to mean find the derivative of this stuff, whatever stuff is inside here. And so then this would be like 2x plus 3. We discovered that in a previous video. So that's how to use Newton notation as a differential operator. It's not very common to use it that way. More often, you'll see the Leibniz notation used. Now, Leibniz notation, for a differential operator, we do d over dx. Sort of like you omit the y, where the y would be, and then you put whatever you want to do the derivative of inside the brackets or parentheses that follow immediately after. Okay, so this is where you'd put your like x squared plus 3x plus 1, and this would equal your 2x plus 3. So that's how it works with Leibniz. Now, the fact that this is a differential operator means if you're going to do the derivative of the derivative, it means applying this differential operator twice. That's where this comes from. D squared over dx squared. If you do d over dx and then do d over dx again, it's kind of like you have two of them. You're not literally multiplying them together, but we do borrow the notation of squaring from multiplying two things, the same thing by itself. We do sort of borrow that squaring notation to mean that this operator has been performed twice. So that's where that comes from. That's why the squared is only on the d instead of on the y, because really it's just this part which has been done twice. The y only shows up once. The Euler notation is really easy for differential operator. This is probably the easiest one. This is the one I'll use most often. It's just capital D subscript x and then put parentheses around something. It's like you're applying a function, except it's called an operator instead of a function, because functions usually we think of a function as taking a number input and giving a number output, but an operator takes a function as its input and gives a function as its output. So all of these are called operators. They look like functions, but I tend to use square brackets for operators and whereas parentheses for functions. It just feels good to make some sort of notational distinction. That's not necessary. That's not like something everybody does, but it's something I do. You'll notice I've used those square brackets before when doing limit notation, right? Or whatever, right? The limit is another type of operator. It takes a function as its input and it gives a constant as an output, but or potentially a constant, or maybe a function depending on the context. But it's another type of operator. Limit. Later this semester, so we have the limit operator, we have the derivative operator. These later this semester we'll also learn another process called integration, and that also is a type of operator. Okay. There we go. That's the video on notation.